India's coastline stretches over 7,500 kilometers. This geography represents a primary engine for the country's Viksit Bharat 2047 net zero targets. Harnessing that potential requires specialized engineering capable of withstanding harsh offshore conditions, an area where Norway has maintained a technical lead for decades. The transition to a green economy relies on frontier technologies like offshore wind and carbon capture. Currently, the high baseline development costs of these systems act as a bottleneck for rapid deployment. On May 18, 2026, the Council of Scientific and Industrial Research and the Department of Scientific and Industrial Research met in Oslo to sign 5 landmark agreements with Norwegian scientific bodies. These memorandums move past high-level climate pledges to establish multi-year programs with specific research targets and concrete funding commitments. We are analyzing these 5 agreements as the interlocking components of a single coordinated R&D to deployment pipeline. Mastering international technology transfer involves engineering a system that connects foreign academic theory directly to domestic industrial hardware. This pipeline begins with foundational research. Here, the shared human infrastructure of the partnership is built. Agreement 1 with the Research Council of Norway mandates capacity building across specific sustainable development goals. The target themes are defined: climate, clean energy, oceans, and health. Agreement 4 brings in the Norwegian University of Science and Technology, or NTNU, to work alongside India's AICSIR in a joint declaration titled Science for the Green Shift. This pact establishes student and faculty mobility programs, specifically targeting the domains of ocean science and civil engineering. Academic mobility serves a practical industrial goal. Complex marine engineering requires a workforce trained on synchronized technical standards. Without this shared scientific language established in Agreements 1 and 4, the downstream industrial deployment of technology is likely to fail. Moving from the classroom to the ocean requires confronting the unique geophysical realities of the Indian coastline. This stage is governed by the 5th Agreement, a 5-year memorandum between CSIR and GRI and Emerald Geomodeling. Decades of Norwegian data modeling, calibrated for the Arctic, must be recalculated for India's tropical subsurface conditions. The deliverables of this MOU include joint research, geophysical survey planning, and technical advisory services for large-scale infrastructure projects. This agreement explicitly includes business collaboration, moving the scientific data closer to commercial application. Accurate, localized geophysical data modeling is a mandatory prerequisite. It is the necessary first step before any physical hardware can be placed in the water. The 3rd phase focuses on applied industrial research through a collaboration agreement with SINTEF, Norway's premier independent research institute. The technical scope here is highly specific, focusing on the circular economy, waste valorization, and carbon capture and utilization. The mechanism of execution mandates the creation of shared innovation hubs to facilitate the transfer of technology. These hubs will interface with existing Indian institutional capabilities, such as those at CSIR IGIB, where work on bio-based processes is already underway. These environments allow prototypes for carbon capture and bio-based manufacturing to be physically tested before they are scaled for industry. Agreement 2 converts theoretical environmental models into testable, scalable industrial processes. The final pillar of the pipeline is Agreement 3, a project-specific collaboration on ocean energy and offshore wind. This is the only pact with a specific, publicly disclosed financial commitment from the CSIR, a total of 341 lakh rupees. These funds support research into floating offshore wind technologies, managed jointly by 4 CSIR institutes and the SINTEF Northwind program. This chart shows the levelized cost of energy, or LCOE. Currently, offshore wind is significantly more expensive than onshore alternatives due to higher capital costs and operational risk premiums. The agreement attacks this cost disparity through joint research on component standardization and physical pilot demonstrations. Proving technical viability through pilot programs is the fastest way to strip risk premiums from institutional project financing. Reducing the LCOE through targeted, funded R&D is what makes the large-scale national deployment of offshore wind in India commercially viable. When viewed as a single architecture, the May 2026 Oslo agreements function as a unified system for technology transfer. The placement of innovation hubs and pilot demonstrations is a deliberate effort to manage the transition from research to industry. In climate technology, the Valley of Death refers to the phase where academic research fails due to a lack of industrial testing or funding. The CSIR-DSIR pipeline addresses this by hard-coding industrial deployment and concrete funding timelines into the initial scientific agreements. By systematically porting Norwegian marine expertise through this 5-stage framework, India has built the technical foundation required to turn its 2047 energy goals into physical infrastructure.